For this lesson, we're going to be taking a look at the idea of solving equations that involve exponential relationships. So it is possible, it's not always easy, but it is possible to use algebraic methods to determine exact solutions for exponential equations. The key to this is that we are going to want to make sure we write our equation so that we have the same base for the exponents or for the powers. Um, we can also try some other things as we go through this, using techniques that we've looked at in the past. For example, if we can use some of the techniques from linear systems, solving by substitution or solving by elimination for systems of equations, and we might get quadratic relations that we might solve by factoring, looking for the zeros. You might even have a situation where you need to incorporate the general quadratic formula. So rather than continuing to just talk about this, let's go ahead and take a look at some examples. I'll start off with something quite simple, and then we're going to ramp up in the difficulty. So the first one I'm going to start with is going to be 2 to the x is equal to 16. Now, if at all possible, and for all of the examples that I've given you here, we want a common base. So 2 to the x equals 16. We can't turn 2 into 16 very easily, but we can turn 16 into a base of 2 because 16 is 2 to the power 4. And if 2 to the something equals 2 to the something, then it stands to reason that those things must also be equal. So if you've succeeded in writing it this way, same bases on both sides, and they're equal to each other, then you can say that this equality implies that x must actually be equal to 4. And that's what we're looking for. So this symbol mathematically means it implies that x is equal to 4. 3 to the 2x is equal to 81. Now, this one is still not particularly difficult, but depending on where your mental math skills are, you might not look immediately and see that 3 and 81 have anything to do with each other. But you might recognize that 81 is actually 9 times 9. And then you get there very quickly. You recognize that 9 is 3 squared and the other 9 is 3 squared. So we've got 3 to the 4. So slightly more complicated here because we've got 3 to the 2x equals 3 to the 4. And we just have to solve a simple little linear equation. If 3 to the 2x is equal to 3 to the 4, then 2x is equal to 4. Divide both sides by 2, and we end up with x is equal to 2. Taking another step up in complexity, base 5, 5 to the 2x minus 1 equals, now 125 is 5 cubed, so that means 1 over 125 is 1 over 5 cubed. So 5 to the 2x minus 1, the way we can deal with this is instead of 1 over 5 to the positive 3, I can rewrite that as 5 to the negative 3. And now that I've written that, I have the same bases across the equal sign, so that means this implies that 2x minus 1 equals negative 3. 2x is equal to, if I add 1 to both sides, I end up with negative 2, and divide both sides by 2, and I end up with x is equal to negative 1. And for the most difficult, at least out of this round of examples, I have 36 to the 2x plus 4, and that is equal to the square root of 1296 all to the x. Once again, maybe you see this and maybe you don't, but at the very least you should be considering the fact that most of the questions of this type, as unrealistic as this sounds, most of the questions you see of this type are actually designed to give you fairly nice answers. So you might start with the suspicion that, well, I wonder what's the square root of 1296, or what is 36 squared? and you're going to get your answer one way or the other. So 36 squared is 1296. So I end up with 36 to the 2x plus 4. So the left side is unchanged. And I'm going to take my time here. Instead of 1296, I'm going to write that as 36 squared. But it was 1296 to the x, which means that 36 squared is all to the x. And then that whole thing is under the square root. 36 to the 2x plus 4 equals, now what else can I do here? Well, 36 squared to the x is the same as 36 to the 2x, and I can take that square root and I can actually rewrite that as to the exponent 1/2. 36 to the 2x plus 4, unchanged, so far anyway. And now once again I have a power to a power. So it becomes 36 to the 2x to the 1/2 means multiply these exponents together. 2x times 1/2 is simply x. And now we are ready to say this implies that 2x plus 4 must be equal to x. I'm going to bring the x over to the left side. 2x minus x is x. Then I'm going to bring the positive 4 over to the right side, and we end up with x equals -4. Okay, same idea, but now I've introduced, notice that there is a quadratic in this exponent. So I'm still going to use the same principles. So I'm going to rewrite the left side. Nothing I can do with that for now. So that becomes 2 to the exponent x squared plus 2x. But I'm going to take 1 over 2, and I'm going to rewrite that as 2 to the -1. That implies that x squared plus 2x equals -1. If the bases are the same across the equal sign here, 2 to the something equals 2 to the something, then those things must be equal. And I'm going to rearrange this all to one side. I'm trying to solve for x. The way I would normally do that in the case of a quadratic is I'm going to rearrange it to one side and then find out what makes this equation true, which means what are the zeros. In this case, this is a perfect square, so this is x plus 1 all squared equals 0, and that's going to be equal to 0 when x is equal to -1. For our next example here, this one's quite different, and a lot of students run into this one and they run into problems. If you're very creative in your problem solving, you might be okay. I'll give you a hint here in case you're trying to get this done yourself. So the first hint is I'm actually going to rewrite this. I'm going to reverse the order. So this is 2 to the 2x. Let me write something over here in the rough. 2 to the 2x. We could rewrite that as 2 squared all to the x, because 2x is the same as 2 times x. Or we could also write that as 2 to the x all squared. And it turns out that it's the second form that is going to be useful to us. So 2 to the x all squared minus 2 to the x is equal to 12. And if that's not enough of a hint for you, now let me go to the next step, which is I'm going to make what's known as a change of variable. I notice that I have something squared here. I have something to the power 1 here, and then I have a number. And if I say let a be equal to 2 to the x, and you're going to see in a moment, I replace 2 to the x with a, and I end up with a, but it was 2 to the x all squared, so that's a squared, minus 2 to the x gets replaced with a, equals 12. And if I bring that over, everything over to the left side, I end up with a quadratic equation. In this case, it's a quadratic equation involving a, but we're going to relate that all the way back to our original definition because the question wants us to solve. It doesn't say this here, but the implication is the question wants us to solve for x. So first now, I'm going to solve for a. I'm going to put this in factored form, and that is a minus 4 a plus 3 is equal to 0. That gives me two solutions. That gives me a is equal to 4 or a is equal to negative 3. But don't forget that a is actually 2 to the power x. So we get 2 to the x equals 4, 2 to the x equals negative 3, and this one is something we need to think about. Now there are a number of ways that you can think about it, but I really like to think about graphs, and I like to encourage students to think about graphs. What does the graph of 2 to the x look like? It has a horizontal asymptote at y equals 0, and then it looks something like that. It's always increasing. We've got this horizontal asymptote at y equals 0. If we talked about domain and range, we would say the domain would be x member of R. It's all real numbers. If we talked about the range of this particular graph, it would be y member of R such that y is greater than 0. And there is the source of my concern, y greater than 0. But this one is basically saying I want 2 to the x to be a negative number, which would be somewhere negative 1, negative 2, negative 3. Well, does 2 to the x ever come down here? And the answer is no, it does not. This is the graph of 2 to the x. No, it doesn't. So this is an inadmissible solution. So this solution is no good, so we don't bother proceeding anymore. We write inadmissible, or we use inad for short. Or another thing we might say here is we might say reject 2 to the x, and maybe I should say reject since 2 to the x is greater than 0. So I'm basically saying I'm throwing away this branch. 2 to the x equals 4. Well, it can be equal to 4. That's a positive value. This seems valid. And now I get 2 to the x equals 2 to the 2, which implies that x itself must be equal to 2. Quite a bit more involved, as you can see. All right, how about this one? Not terribly complicated if you've gotten a good feel for what we're doing here. This one seems straightforward enough. 8 to the x plus 4. I'm going to rewrite 8 as 2 cubed, but that's all to the x plus 4. And then this one is 2 to the 6. I don't quite have a base equals another base yet. There's still some complexity here that I need to deal with, so I'm going to rewrite this as 2 to the 3 times x plus 4, multiplying out the exponents, 2 to the 6. Now I have a base equals another base, and this implies that I'm going to write it, 3x plus 4 is equal to 6. So I multiply, I distribute that, and I end up with 3x plus 3 times 4 is 12 equals 6. I end up with 3x equals negative 6. I end up with x equals negative 2 as my solution. All right, this one is particularly strange. You've got 48 here. Well, 48 is definitely not, well, 4 squared. 4 squared gives you 16. Multiply that again, you get 64. So what do we do here? And the answer is the first thing we actually do is we divide both sides by 3. I can't tell you a particular rule here. You just have to try different algebraic options, valid options, and see whether or not they take you in a useful direction. And practice and experience, you'll start to get better at choosing those options. So if I divide both sides by 3, I end up with 4 to the x. 48 divided by 3 is actually equal to 16, which means 4 to the x is equal to 4 squared, which means that x is equal to 2. So it ends up actually being quite a short and simple solution, but when you first look at it, it might look more complicated than it really is. There's another technique that we can use when things aren't going to work out exactly, and that's called guess and check. So guess and check is where you make repeated estimates, but you don't just want to be estimating blindly. You want to be making educated estimates. So one thing you might want to look at in this case, here we've got 2 to the x. So what are powers of 2? Well, we know that 2 to the 1 is equal to 2, 2 to the 2 is equal to 4, 2 to the 3 is equal to 8, 2 to the 4 is equal to 16. And so we can see that 9 fits in between the 8 and the 16. And so that means our answer, x, is going to fit in between 3 and 4. And so what I can now do, and it actually looks like it's going to be closer to 3 than it is to 4, because 9 is closer to 8 than it is to 16. So now with guess and check, what you do is you try different values. So I'm going to try an x value and then see what my 2 to the x value is that comes out of that. So what if I try, let's say, 3.1? So when I put 2 to the exponent 3.1, I end up with 8.57. I'm going to try 3.2. I know for a fact that's going to be too big. It's going too far, but I'm still going to try it. So that's going to be, we're doing 2 to the power 3.2. And that gives me 9.19. And so now take a look at these two. Take a look at the difference between these two. We know that 9 is somewhere in between here, but which one is it closer to? It looks like 9 is closer to this one, which means my answer between here and here looks like my answer should be closer to 3.2. And so what am I going to try? I could try right in the middle, 3.15, but I think it makes sense maybe to try something a little bit higher. How about 3.18? And so I do 2 to the power 3.18, and I'm getting pretty close, 9.06. How about 3.17? 2 to the power 3.17 equals, and that's really quite close, 9.00. So if I kept putting out decimal places here, yes, this is not exactly 9. This is not an exact answer, but this is a pretty good answer. Therefore, x is approximately equal to 3.17. Another way that I might specify this is I might say solve by guess and check, and I might say to this many decimal places. So for example, the answer that I've got right here is a good solution to at least 2 decimal places, because it looks exactly like 9 for those first 2 decimal places. So let's do the same thing here. Now before we get into any of our actual algebra parts here, let's go ahead and figure out our guess and check part. So you can do this in your rough work, or you can just say, okay, I'm going to say 3 to the y equals 25. And then I think of powers of 3. 3 to the 1 is equal to 3. 3 to the 2 is equal to 9. 3 to the 3 is equal to 27. So I'm between these two. And so what am I going to try, and what value does that give me? So I'm going to try something close to 3, bigger than 2. So how about I try 2.9? That's quite close to 3. So now I do 3 to the power 2.9. And that gives me, surprisingly, a little bit too low. That's 24.19. So how about 2. Well, that seems awfully close, but you know what? Let's just split the difference. 2.95. I know I can't go to 3, so I'm once again 3 to the power 2.95, and that gives me 25.56. So we're really getting quite close. So I need somewhere in between. Which one am I closer to? It's actually pretty close in between. So how about 2.93? I want to be a little closer to the 9.5. 3 to the power 2.93 gives me, and that hit it, 25.00 again. So this one is good, and I'll write out a couple of extra decimal places, 0015. So if I had asked for this to be correct to one decimal place, yes, that would be good. To two decimal places, that would have been good. To three decimal places, I would have had to keep refining my answer. Now understand, in this case, I'm not quite done. I'm going to use 2.93, but now I have to say that 3 to the 2x minus 5 is approximately equal to 3 to the 2.93. So remember, we're trying to say that 25, and that's what this is saying, 25 is approximately equal to 3 to the power 2.93. So where I had 25 before, I'm going to replace that with 3 to the power 2.93. But now I can say that that implies 2 to the x minus 5 is equal to approximately 2.93. 2x is equal to 2.93 plus 5, so that's going to be 7.93. And then x is approximate. Don't forget, these are all approximate. And then 7.93 divided by 2 is 3.965. So this value of x gives me a value that's good to two decimal places using guess and check. Okay, so that's it. Relatively short lesson, straightforward, just requires you to apply some different skills and look at some things in a different way.